Okay. Alright. What we're going to do today is we're going to go over some of the problems. These problems are not all that difficult. It's mostly plugging into equations. We still have to do the hand stuff though to figure out some of the directions. This stuff, we'll go over one problem like that on here. I'll figure one out here, and then we can go over it with that, and then we can go over that if you guys want to make some review sheets maybe for later this week. Okay. All right, let's go through what these equations mean and all the variables. So our first one is force on a charged particle moving through a magnetic field. Alright, so for that one we have F is equal to the force. What's force measured in? Newtons. What's Q?
Charge.
Charge. What's charge measured in? Coulombs. So that's abbreviated capital C. What do you think lowercase v is?
It's the magnetic field. Force.
What's lowercase v been in the past?
They said
Velocity.
Velocity.
Mustache is talking.
There you go. Okay. So lowercase b is velocity, and capital B as in boy is magnetic field. So magnetic field is going to be measured in Teslas, so it'll be abbreviated capital T. And one other thing you guys should know is the charge of a proton or an electron is 1.6 times 10 to the negative 19th coulombs.
I'm sorry, can we just,
You want me to go through it again?
maybe just last part?
Okay, so the charge of a proton or an electron is 1.6 times 10 to the negative 19th coulombs. Okay, next one, force on a current carrying wire in a magnetic field, F equals BIL. Okay, so F is still force. What's capital B? Magnetic field. What's I? Current. What's current measured in? Amps. And what do you think L is?
love.
Not love.
I know love one's class.
It's
Length of the wire.
length of the wire in meters. Alright, and last one, this is the magnetic field due to a current carrying wire. So the one above it is the force on a current carrying wire. And remember the force on a current carrying wire, so if there's already a magnetic field and there's a wire with current going through it, that's when you use the flat hand, right hand rule. So your hand flat like this. When you're trying to find the magnetic field due to a current carrying wire, it's the curl one. So this is the curl one to the magnetic field due to a current carrying wire. B is magnetic field still. That mu naught is a constant, and in this equation it's kind of a silly constant. The constant for mu naught is called the permissivity of free space. The constant is 4 pi times 10 to the negative 7th. So you see what's going to happen every time you use that constant? It's going to cancel out. The pi's are going to cancel. So it's silly in this case, but in other cases there's no 2 pi underneath it. What's I again?
Current.
Current measured in
Amps.
amps. And D is the distance from the wire in meters. D is the distance from the wire in meters. Alright, any questions on any of those equations? Alright, number 1. An electron moves north at a velocity of 5.1 times 10 to the 4th meters per second and has a magnetic force of 6.4 times 10 to the negative 18th newtons west exerted on it. If the magnetic field points upward, what is the magnitude of the magnetic field? Anybody remember what magnitude in general means? Size, not direction. So if it just asks for direction, or it just asks for magnitude, you do not need to include a direction. In this case, it tells you what the magnetic field is pointing anyway. So which equation are we going to use? F equals quv or F equals BIL? Quv. So you can use F equals quv.
What was
Those
that
rules
last
the time.
time?
I knew a girl in college who had no vowels in her last name.
What was her last name?
SRP, Kate Serp.
That's so weird.
That's weird.
Alright,
What country?
she was from America, but she was something Eastern European. I forget what the actual nationality of her name was. Okay, what's our force?
Force is 6.4 times 10 to the negative 18th newtons west.
4 times 10 to the negative 18th newtons west. We don't need to include that. Alright, what's the charge of an electron?
1.6 times to the negative 19.
Is the charge of an electron positive or negative? Negative. We are going to leave that out here though. We just kind of want the absolute value of the charge because if we're looking for like how it's interacting with something or its direction, we're going to use our hands. So just to keep it straight, we're just going to have force always be positive and then we'll figure out the direction with our hands. Does that make sense? What's the velocity of the electron?
5.1.
Times 10 to the 4.
Okay, how about we not say it all at once at different times?
5.1 times 10 to the 4.
Well, you guys like will all start to say it, but you have to say it like a second differently, so it'll be like 5, 5, 4, 1, 1. I can't understand what you're saying. And we're looking for a B.
Sounds like you're mad.
So when you solve for B, what do you get? Jason?
.84 times 10 to the negative 12.
Really? No.
7.84 times 10 to the what?
Negative 4.
And what's the units for a magnetic field? Teslas, and it's abbreviated capital T. That's our answer. We don't need direction with that one.
Oh, yeah, I didn't get that.
Yes.
Even though you don't need the directions, why when you try and do this with your
Better.
does it not work?
Because it's a left hand, because it's an electron. Alright, any questions on this one?
So that's the answer.
That's the answer. These are, like I said, the math in these is pretty straightforward.
Wait, how do you, what unit is this?
Teslas.
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 Never heard of it.
Can I erase this?
Must be made up.
Alright. Next one. A wire carrying a current has a length of 0.14 meters, and the wire experiences a force of 3.67 newtons south, and is in a magnetic field of 1.14 teslas pointing up. What is the magnitude and direction of the current?
F-bill.
So we're going to need to use F equals BIL, and what kind of rule are we going to use to find the direction? Flat hand, which hand? Right or left?
Right.
Right. So we're going to use our right hand flat. Let's find the magnitude of the magnitude of the current first, and then we'll find its direction. So we're using F equals BIL. And what's the force? 3.67 newtons. What is the magnetic field?
1.14 Tesla.
1.14 teslas. Current's what we're looking for, and what's the length of the wire?
0.14 meters.
1.4 meters. So when you solve for I, what do you get? 22 point, I think it's 22.99, we'll call it 23 amps. Okay. Everybody okay getting 23 amps?
Yes.
Alright, so now. Experiences a force to the south. So what do we point to the south? Palm of your hand to the south. And magnetic field is pointed up, so what points up? Fingers. So what direction is the current? East. So it's 23 amps.
Can we do that again?
Yep.
Yeah, slow motion, please.
Okay. So force is to the south. So right hand and palm to the south.
North south equals right hand.
No, current equals right hand. So point your palm to the south. And fingers up. And what direction is your thumb pointing? East. Does that make sense? It kind of vibrates when I talk. It's kind of disconcerting when I'm looking down. Alright. Anna brought it.
She made it.
Okay. Alright. Number 3. This is probably the most difficult, like in terms of math, because you have to use 2 equations, but it's really not that bad. A wire is carrying a current 6.1 amps to the north and is 11.1 centimeters away from another wire that is carrying current 6.5 amps south. Each wire is 2.7 meters long. Find the force one wire exerts on the other if the force is attractive or repulsive. Okay. So first thing, do you guys remember from the notes, if we have 2 current carrying wires, do they attract or repel?
If they're going the same. Depends what
It depends what direction they're going. If they're going the same direction, what do they do?
track.
Same direction they repel.
I don't know.
Okay. We're gonna draw it up here because it's a good review anyway. And hopefully you'll remember it then. So let's say they're going in the same direction. Actually, they're going in opposite directions in this one, so we'll do that, just an example. So you have one going north, one going south. Okay. What we need to do to figure out if they attract or repel is find the direction of the magnetic field of one of them and use that magnetic field to figure out the direction of the force on the other. Does that make sense, everybody? So we're going to use the bottom one. We use our fingers curling around. So at the other wire, what direction do our fingers go? Do they go into the board or out of the board? Into the board. Does everybody make sense with that? So I'm going to draw a couple X's here. So magnetic field is going into the board. So what do we point into the board with our right hand? Fingers go into the board. And what direction does our palm point? Or what direction does our thumb point?
That way.
To the right. And so what direction is our palm pointing?
Up.
Up. So the force on this is up from the other wire. So are these attracting or repelling? Repelling.
Not in the first one.
So in this case, they're opposite directions, so they repel. So now let's actually do the math. So that's going to be our direction. It's going to be repelling. Okay. So first thing we have to do is figure out the magnetic field from one of the wires. Do you want to use the 6.1 amp wire or the 6.5 amp wire? 6.1. Alright, so we have to find the magnetic field due to a wire, we do magnetic field equals mu naught over 4 pi, or 2 pi, thank you. 2 pi times I over D. So B equals 4 pi times 10, so negative 7th, over 2 pi times current, which we said is 6.1 amps. And what's the distance between the 2 wires? 11.1 centimeters.
Oh.
How many meters is that?
0.111.
So 0.111 meters for our distance between them. Alright, make sure you enter the exponents into your scientific notation stuff into your calculator, right? That's where you guys mess up a lot in math. And what did you guys get for magnetic field?
1.09 times 10 to the negative
0.09 times 10 to the negative 5th. What's the unit on that?
T.
Teslas?
I had to the negative. Yeah, Abby said
3.5
that.
times 10 ratios.
You guys entered in, right?
What?
I got what Kyle got.
This is what I got as well, and the other class got as well. So if you guys are having a lot, this creates issues in your calculator for everybody. For some of you.
Yeah, I got it.
Why can't you
Guys,
just cancel?
you can cancel out the pi's, and you end up with 2 pi times 10 to the negative 7, or 2 times 10 to the negative 7. Alright, so now we have the magnetic field. What are we going to use to find the force on one of the wires? F equals BIL. So our force is equal to magnetic field 1.09 times 10 to the negative 5th Teslas. What's the current? Which current are we going to use since we're looking for the force in the other wire? Yep, so 6.5 amps. And what is the length of the wires, or of both wires? 2.7 meters. So what's our force? 1.9 times 10 to the negative 4th newtons. Okay. And did we say that's attractive or repulsive? Does that make sense to everybody?
Yes.
Can we go over how it's not repulsive?
Sure. The easy way is if they're in opposite directions, it's always going to be repulsive, and in the same direction, it's always going to be attractive. If you want, we can do
No, that's fine.
is that enough? Or you can figure out what way the magnetic field's going, and then use your flat right-hand rule to find out what the force is. Okay. Again, these math problems are not that difficult. The hardest part of these tends to be the rule things. Why don't you guys do you guys want to go over any of the right-hand rules before you start on this? Which do you guys want to do? I think most people are having trouble with this one,
Yeah. Yep.
the curl stuff. Okay, I'll just make up some random problems here while we're doing it, but before you get started on that. Alright.
I don't use the same way you do.
Okay, so let's do this one together real quickly. Current's going north. What is the magnetic field on the bottom of the wire? So everybody try it, and I'll go over it together. This is a curly hand one. It is west. So you take your thumb, point it north, so toward the board in this case, curl your fingers, and what are your fingers doing on the bottom? Going to the west. Does that make sense to everybody? You guys want to try another one kind of like this?
Yeah.
West. That's your left hand, Kyle. Okay. Now our current's going east. What is the magnetic field on the north side of the wire? Remember, the sky is not north, Sarah. It is up. So, thumb to the east, and you put your fingers on the north side, and they're pointing up on the north side. If you guys want to do more, just get started on your problems.
You just want to sleep.
Keep going.
Just like
One more.
Okay, so current's going down. What is the direction of the magnetic field on the west side of the wire?
North.
North is correct. You guys feel like you're getting this?
Yeah. We're good.
Alright, can we, you guys feel okay about this stuff now?
Yeah, I get it.
Alright. I'll come around, I have the answers up here, I'll come around and help you with these problems. Just let me know if you have any questions.